All right, thank you. I'm going to talk about Kompics Scala, which is DSL, an embedded DSL for pretty much for teaching distributed systems. All right, and the goal of it was to somehow reduce the intellectual gap between reading abstract descriptions of algorithms and transforming them into code that you can actually go and run in the world. And I'm going to talk about from an education perspective here. And if you remember your time at some university, I suppose you all went to some at some point, usually courses start with a course book. And in our case, it is this one, Reliable and Secure Distributed Programming. And it's a very nice book, and the important part in it is not the text, actually. It is these beautiful graphics with code. And it's not real code, it's studio code, right? This is actually what we primarily use the book for, and I use it to this day when I have to look something up. So what you get is these really nice, very concise descriptions of algorithms in a pretty high-level way. And you can see this one is a basic broadcast. It's a super simple algorithm, pretty much the simplest thing you can think of. You want to send a message to a bunch of nodes, and you simply start by taking a list of each nodes, iterating through it, and sending each one a message, and on the other side delivering it. Okay? This has exposes an interface, if you will, and that interface is best effort broadcast. Gives you some guarantees. I'm not going to talk so much about the guarantees. Basically, we're not going to make messages up, and we're not going to duplicate messages or something. It's not really what I want to talk about. What I want to talk about is that it also specifies the messages that this interface actually sends and accepts. So the request message basically that interface accepts is broadcast, and it says broadcast message M to all the nodes. And the reply message that you can get if you're using this interface is deliver, which says I got message M from some process. Additionally, the algorithm also uses some kind of dependency, if you will, so another abstraction below it. And that abstraction is the perfect point-to-point link, which you can very simply think of as a more fancier TCP. And that interface also gives you two messages that are important, and one is send message M to a process, and the other one is deliver, which looks exactly the same as up there. Okay, and then once you have this, you can basically read the whole description of the algorithm. It tells you I implement this, I use this, and if I'm supposed to do a broadcast, just send it with the network link to everyone, and if I get something from the network delivered, simply deliver it to my local node. All right, now there are students that prefer nice pictures instead of text, so you can just as well go and draw this. And if you want to interpret my beautiful box model here, basically the blue boxes are components, which you can see as algorithm implementations. We have our basic broadcast implementation here that corresponds to this algorithm. And somehow, since we're using some implementation of point-to-point, we don't actually know which, we treat this as a black box. All we know is that it implements perfect point-to-point link, right? And the green boxes then we call ports, if you will. These are the interface abstractions, and you connect the ports with channels, and along these channels you can send messages that go in a specific direction. Okay, zooming into the component, you have these parts basically that you have to map. So the triangles are called handlers, and they are in fact then what will contain the code that is being run. Handlers are connected to the port abstractions by subscriptions, which are black arrows here, and the subscription is pretty much implicit here. In the algorithm you see that it just says the port where the message is supposed to come in on, and this implies a subscription of the handler to the port. And in more complicated algorithms usually you also have some kind of internal state. Basic broadcast doesn't really use any state except maybe the pi, which is the set of all messages, though it kind of treats that as if it's global state, not local state. But for a reasonable implementation, you probably want to treat it as local state. Okay, now that was the model, right? That is what we teach our students as a model. Now from there, somehow they have to get it into executable code. And what we've used now for many years for this process is a Java library called Kompics Java that is one possible implementation of this logical model. And if I give you the Java implementation for this code, you will not be able to read anything because it's this long. For a trivial algorithm, I might add. Okay, but I will tell you a bit what part is what. Up here, they're just event definitions. So technically, I don't show them here. Maybe I'm a bit cheating. I showed you before in the other definitions how the messages look. That takes up a fair chunk of this blob of code. Then there's a port definition that just says that these messages go over the best effort broadcast code port. And then down here, this part is the only part that actually maps into this algorithm, if you will. So let me zoom in a bit on that one. But what you can see already here is somehow how these parts map. And I'll zoom in a bit so you can see it better. So you can see that up here is more or less the equivalent to this part, where I say, okay, I'm providing this port, so this is what I'm implementing with abstraction, requiring the other one. This part and this part is more or less boilerplate code. You see, it doesn't even map to anything in the abstract algorithm. And the actual handler implementation, so once you get down here, you're pretty much exactly at the level of the algorithm. So here it's fairly readable. This part, however, is relatively verbose, and it's just like telling Java the types that the handlers are supposed to be and things like that. And another fun part is that you have to subscribe them explicitly up here. So this one just says take this handler and subscribe it to the BAP port and the other one to the PL port. So this is adding these black subscription arrows explicitly. And another thing that I find rather jarring about the Java implementation is you have this beautiful pattern matching on the fields of the messages in the abstract algorithm, but of course Java can't do that, so you have to do field accesses for them, which is rather ugly. All right, so I wanted to make this better, right, because this is not beautiful for students. And in fact, actually, I started writing this after I took the course as a student, and I was like, holy, what the hell, why do I have to write all this damn code for something very simple? So the goals then of the re-implementation were basically avoid Java's verbosity and also have runtime compatibility, because we do actually have a lot of code for exercises already written in Kompics Java, and it would have been a lot of work for a TA to just redo all of this at once. So it would be rather nice if we could run both of them at the same time. And that is, of course, the point where Scala usually jumps in. If you want a better Java, but you still want it to be compatible, then, oh, Scala, here. Right. Another thing then that jumped out was we want pattern matching support, because that will give us a better match with the algorithmic specification. I can do some renaming. That's not really Scala specific, but some things weren't maybe named optimally in the original implementation. And there's the #1 bug in Kompics Java is forgetting to subscribe your handlers, because you have to do it in a separate place, which is very, very confusing. And like people who have been using this for 7 years or something still do this occasionally. And then you're very confused because you don't see anything and you don't know why. So that we also wanted to get rid of. And I'll just jump ahead now and show you the result of this process. The result is this Kompics Scala DSL, which first of all stands out by the fact that I can actually show you the whole code in a readable manner on one slide. You see the message definitions basically have come down to one, well, I skipped one message, so 2 lines maybe, thanks to Scala's amazing case classes. The port definition looks pretty much the same, except that we can now use objects, which really in Java, they should all, I mean, they've always been singletons. Now we just have a nice statement to make that explicit. But then the actual mapping of the class, you see there's almost no boilerplate anymore, except this one definition, which you can do in this really beautiful way. And thanks to whoever reviewer pointed out that you can write it like this, because that is really awesome. I didn't know. And then if you read the actual handler definitions, they are very, very similar to the actual algorithm in the pseudocode, right? So you still have the upon event, change a bit the order of the port. I actually like this better than the pseudocode. And then you just have a case statement, you pattern match the broadcast message, you do the for each, and you trigger with the port on the right-hand side of an arrow using Scala's arrow to tuple conversion. And that is a lot more readable. So let's go back for a moment and check that we actually implemented the design goals, right? So first of all, we wanted compatibility, and if we want to use both of them in the same project, that means we need to have separate namespaces for them. So the Scala version actually resides in a slightly different namespace below the Java version. We have automatic handler subscription. There's no reason to do the extra subscribe port anymore. It's automatically done when you do the port upon event. And we have pattern matching. You can directly use the values here down there to create the new object, which in this case actually happens to be exactly the same. We could just have forwarded the object. And it is a lot shorter than Java. All right, so this is, if you count, these are not exactly 28 lines, but in the file it's 28 lines of code. The Java version for this is 52 lines of code. And this generalizes to other algorithms as well. So if I just looked it up for a bunch of common distributed algorithms, it doesn't really matter if you don't know what they are. The point is that the atomic register has about 90 to 118 lines. It's actually not such a big difference, and the reason is that I didn't count the message definitions in here, which make up a huge part of these numbers. An eventually perfect failure detector is 83 lines in Scala, 175 lines in Java for something that is also actually pretty simple in terms of algorithms go. And then if we jump up to the big juggernaut algorithms, pretty much the most complicated thing we teach in the course is a sequence Paxos, which is a consensus algorithm for agreeing on executions, for example, in a database. In Scala, I can do this in about 180 lines of code. In Java, the same implementation eats like 700 lines of code. So obviously, lines of code is not the only indicator of code readability, but it's one that's pretty easy to quantify, and I think I made my point on that here. Okay, so now if you're paying attention, you're probably angry with me because I've not told you something, and I haven't told you what that is. What is this handle doing there? Why is it not just the code that I want to execute on the right side of the statement? Before I can tell you this, I have to tell you something about how scheduling works in Kompics. First of all, if you have a bigger setup of components, for example, a network component implemented by Netty usually in Kompics, and a bunch of components that use network, all of them are connected to the same network component, and when a message comes in over the network, it's going to get broadcasted to all the connected components. Okay? In Kompics, there's no addressing. That is the major difference between Kompics and actor systems, is that actor can be addressed while Kompics components cannot be addressed. The only way to get messages to them is via connected channels. Okay, so that means all events are always broadcasted along all channels. What that means for scheduling is that we very, very frequently get messages on components that those components are not actually going to handle. And that means we actually need to avoid scheduling them, because there's no point in throwing a component at the scheduler and then running it just to figure out afterwards that, oh, we're not actually doing anything, we're just throwing this away. Okay? This is a very common case in Kompics, especially in network-heavy applications. And the way Kompics deals with this in the Java world is that it matches events first before scheduling. What I mean with that is, say I trigger an event, it travels along a channel to a component. It will do this on the thread that originally triggered it, so on the sending components thread. And when it arrives there, I do a check whether or not there are actually any handlers for this particular event on that component. And only if this check succeeds, I will stop there. I will send the component to the scheduler, wait for it to be executed, and then take the event again, actually run all the handlers that deal with it. So here, I basically only have to find one match. It doesn't matter if there are multiple handlers that will deal with this event, because as soon as there's one, I have to schedule it. And then once it's scheduled on the new thread, I will go through all of them, and I will execute all of them. And to make this more efficient, you will probably execute multiple events at once when you go through all the effort of scheduling the component. All right? And what that means is that there's a level of indirection between where we match events and where we execute handler bodies. And that is what we also needed for the Scala implementation. And there were basically two options to do this. One is to use Scala's built-in isDefined. And this has the advantage that it has no storage overhead. I mean, I anyway have to store the event on a queue while I'm scheduling. And apart from that, I don't have to do anything. And I can again do just until the first match and then run it. But the downside of this approach is that if the pattern match is actually a fairly complicated match statement, I'm going to do the work twice. Most of the work, at least twice. Right? I'm doing it once on the sending thread, and then after scheduling, I'm doing it again completely on the thread where the component is being run. An alternative to that is that I only do the matching once, but during that, or after being done with that, I create a closure in which I store the matched values, so then on the receiving side, I simply have to run the closure. And that is in fact the version that's currently executed, and that is what this handle basically means. It is nothing but a nicely readable way of creating a closure from unit to unit. And this has the disadvantage that we have a temporary object creation. We have to store it. We are throwing work at the garbage collector, but we're only doing the match once. So clearly there's some trade-off between those two things. I mean, at some pattern complexity, the second is going to be better than the first. And it turns out that complexity is about a width or depth of around 3 to 4, right? So case class with 4 fields, that is about when they break even, or a nesting depth of 3 or 4. And when I implemented this, I thought this was would be pretty common and was pretty relevant, so I ended up implementing this one. Today, I'm not so sure that's actually true. I mean, getting there, you will do pretty frequently, but crossing the threshold, you will do pretty rarely, actually. So maybe if I had to do this over today, I would go with the other one, or just allow both. I might actually just allow both at some point. I'm not sure if it will confuse students. In any case, clearly this costs something in terms of performance, even compared to the Java version, which doesn't do this. So then the question became, right, how much do we pay? And to figure that out, we replicated an old akka experiment by Patrick Nordwall, which back in 2012 got 50 million messages per second on akka, which was quite impressive. And the experiment is basically just increasing the load of parallel ping-pong pairs, right? Just sending ping-pong messages back and forth and seeing how long it takes you to do a billion of them or whatever. And the nice thing about this, all the messages are objects, so there's pretty much no garbage collection overhead by the messages themselves. And we ran this on AWS with a 36-core machine, both akka and Kompics using fork join pool schedulers with a throughput of 50 events. And the result is the following. Akka is really performant. I mean, I end up with over 80 million messages per second on this infrastructure, which is very impressive. Kompics is around 50 million messages per second, so pretty much where akka was in 2012. This is the Java version, right? Pretty happy with that, I must say. It's a bit more complicated setup than akka, so I'm actually quite happy with that. And then let's see what we paid in the new version in Scala. You can see down here they're pretty similar, but there's a bit of a scalability overhead here that gets us down to a bit over 30 million messages per second capping out there, and that is most likely the extra work of the closure creation on the sending thread. But quite frankly, for an education system, I mean, 30 million messages per second, almost a million per core, I can live with that. All right, so now I said we're talking about education, and I've kind of talked about a lot about distributed algorithms. So last year we finally got to actually use this for education, and we started out by introducing it in an edX course on distributed algorithms, which had 5,000 enrolled students, and we wrote all the assignments in an environment that used Apache Zeppelin as a front end, and then some automatic testing and checking in the back end, generating grading tokens, and then grading the tasks. And this worked really well. We got very good feedback from the students. It was very easy for them to translate the algorithms to code just because they look so incredibly similar. And this course is also currently being rerun, so if this is interesting to you, just go to edX, check KDHX, and it just started last week. You can still join. And shortly after this one, we also started migrating our on-campus course, which has been running much longer, to allowing students to pick between Scala and Java. I didn't want to just force them to use Scala for now. And this was a course with 44 students on campus. 10 of them chose Scala, and I must say that there was some overhead to doing it in Scala, because I gave them a template for the project that they were supposed to do, but I only gave them a template in Java, because that is what I happened to have lying around. Still, 10 of the students picked Scala, and all of them had very good results for the project. And I got pretty good feedback from most of them, and the few complaints that were there were usually about documentation, because I'm terrible at writing documentation, and they had to use some more complicated features than I just show you, like the simulation framework, which has long been a point of problem for Kompics. Right, so to summarize, we introduced the Kompics Scala DSL with a point of reducing the mismatch between algorithm descriptions and code, making them as similar as possible, and reducing a lot of Java's boilerplate, which was just ridiculously distracting to students before, just having to write so many files and very big event definitions, which gained them nothing in understanding. And we use this for a bunch of coursework now, 2 edX courses more or less, and 1 on-campus course, which will also be repeated next year. And got fairly good feedback from students, and also feedback from myself, because I have to write code, and I much rather write in Scala than in Java. So it's actually nice for us as well to write these tests in Scala instead. And looking a bit of the performance penalty, clearly it's not free. Didn't expect it to be free. Pattern matching is more complicated. The closure creation costs something. But I feel it's quite acceptable for a non-production system to run with 30 million messages per second, and performance is not necessarily the main focus of an education system. Thank you.
In your implementation, did you attempt to use any of the Akka stuff like futures? So like, you know, when you create the closure, maybe you would hand that off to a future and just let it, you know, do its thing. Or do you have your own mechanisms?
Yeah, there's actually pretty similar to how Akka works internally. There's a scheduler. So basically, when I create, I don't hand it off to a future in that sense. I put it on a queue, a concurrent queue. And when the component is scheduled, so I notify the scheduler that this component should be scheduled. When it is scheduled, it will just start pulling out the closures from the queue and running them.
Okay, so just small objects, you're not blocking threads or anything like that?
No, I mean, the whole implementation is running multi-threaded, so the scheduler just gets a thread pool basically to pull from, and then it will schedule components on it. So the parallelism level is basically on a per component basis.
Okay.
So I realized that the goal was for a system for education, right? But you know, if it's nice for students to use, it's also nice for production, you know, for practitioners to use. So, and you know, you've mentioned performance. Are there other factors that would need to be changed for production use?
No, you can totally use this for production. We have code, not yet Scala code, but Kompics Java code running in some sense in production. I mean, by research standards in production.
Okay.
So you can totally do that. I personally have preferences for when I like to use Akka and when I like to use Kompics. Kompics tends to be better for relatively low-level things. I mean, like, not I/O level, but you do just above the I/O level, where you do these very core algorithms like failure detection and consensus and these kind of things. So because in Kompics you have a lot of control over your environment, right? You can pick what network protocol do I want to use, how do I want to match up the events that go over it. I had a paper at ICDCS earlier this year where I was doing machine learning for speeding up transatlantic connections. I was doing this with Kompics because I had the control to tell the network layer to go over TCP or UDP, right? So these are the kind of things where I really like to use Kompics for, and it's perfectly suitable for production in that sense. Once you go to higher levels, like closer to an application server level, where you're maybe serving REST requests or something, there I would go towards Akka because it has a lot of really good support for this and lots of libraries, and it's just much more efficient to write code at that level in Akka. I mean, basically you have to think about, is my problem something where addressing things is very common, or where I'm basically building a protocol stack? Kompics is meant for building protocol stacks, and it's really good at this. Akka is meant for things where maybe you have a router and you want to distribute the work, and it should all work really nicely, and Akka is really good at that. So I actually use them together occasionally. I have an interface library between the two.
Okay. Cool. Thank you.
Hi, thanks for your talk. Actually, I've been looking a little bit in what you're doing. You pinged me at some point. I find this very interesting. So I was wondering, actually, in your best effort implementation, at some point in the Scala implementation, you have this declaration where you say provides, right?
Yep.
And I was wondering, sort of, what are your thoughts on type checking these specifications of these algorithms, and like, how would you do it, and what do you think about it?
Were you at eCoop last year?
No, I don't think so.
I had to talk on exactly that problem at, what was it, PM, Philip knows. The programming languages for distributed processing, whatever. So the point is, yes, this model is absolutely perfectly suited for doing type checking of these things. And I'm actually having 2 projects on this. So what I was doing last year was I basically wrote a compiler. That one was more meant for the Java version yet, not for the Scala version, that does this basically before it outputs Java code and checks these, that the types conform. And right now I actually started doing statically typed Rust implementation of this. That has more focus on performance and not at all on education. So yeah, you can do this really well. You could probably do it in the Scala version as well. I didn't do it originally because I wanted to be binary compatible or runtime compatible with the Java version, and there you can't do it. I mean, it does actually all these checks at runtime. It will actually complain if you're doing the wrong thing at runtime. You try to send the wrong messages. And since I wanted to stay compatible with that, I didn't change how the Scala version actually interprets these types. But it would definitely be feasible to do, and probably a reasonable thing to do at some point for Scala as well.
So I was thinking, like, in addition to type checking the ports, right, and their types that are being sent there, I was actually thinking about type checking, like, sessions, and like properties of these algorithms. Like, for example, in the specification on best effort broadcast, you have a guarantee that messages won't be duplicated, right? Yeah. If the sender doesn't fail, right?
Yeah.
Could you do something in that sense as well? And how would you do that? Like,
So there we're going back into the session types direction, right? So
maybe, yeah.
my typical problem with session types is that they're often very difficult once you have multiple to one or multiple to multiple communication, because it becomes impossible for the type checker to keep track of all the possible combinations. As long as you're doing one-to-one protocols, you could probably do it like this with a type checker. It will work fine. But sadly, that's not the most common case. I mean, the most common case is many-to-one or many-to-many channel connections. So that one, I don't really see, at least not for me. Maybe someone else wants to do it, fine. I don't see myself going that way. I don't think it's a fruitful endeavor. But having the channels themselves type checked definitely straightforward probably, and definitely something I would look into.